Okay, happy Friday. Nice to be here. Probably your last class before you can go and get ready for the football game, unless you're taking physics. Do we have physics people again this year? Sorry. At least it's not me. I'm not the last person between you and physics and the game. Okay, so I remembered to turn on screen capture. I apologize to those who use that. I've forgotten the last 3 lectures, so it will be turned on. A couple quick announcements. First off, on homework, I made an announcement on Canvas about this. On problem 3, I stated that the average stress is 70 megapascals, and you cannot solve the problem if it's 70. That's a typo. It needs to be 170. So that's that. You definitely are wrong. If you did it with 70, there's a problem. If you're in 2010, MSE 2010 students, you have a lab. We've assigned a peer review for this lab, meaning before the TAs grade it, you're going to grade each other's, right? And you will only see that that has showed up if you've submitted your lab already. So if you haven't, you need to do that right away. Another announcement is that there's the SWE, the Society of Women Engineers, that put together a night with industry. And I've gotten a reminder posted on Canvas about that. It's a pretty awesome thing. It's like $5 or something. It's some very cheap amount of money. I mean, that alone for dinner is worth going. But you get to sit with somebody from industry and start networking. Heck, you could get an internship out of it. Who knows? Like, so something worth going to. You don't have to be a girl to go. Just go. Then the last thing is IM Flash. IM Flash makes flash memory. They're huge. Everyone here must know what they are. They're down in Lehigh. It's a mega corporation. We're delighted that they're here in Utah. And every year they host a series of tech talks where they want students to come up with ideas related to a topic of their choosing and pitch basically like a lit review and sort of the frontiers of knowledge. It's usually related to something obviously that they work on. And this year the topic is semiconductors in healthcare. So you would give a pitch about what's the state of the art, what are innovations that are possible, what's the limitations, what are the materials challenges, whatever. In the last 3 years, material science students have dominated this thing and won it. So the gauntlet is thrown down for you mechanical engineers that might want to end up working at IM Flash. Go give a tech talk. A bunch of people have gone on to get internships and even jobs by winning this thing. So that's the announcements for today. So we are going to pick up where we left off, which is establishing a relationship between the size of ions and the lattice parameter. How big is your unit cell, right? We're going to pick up there. We'll then talk about packing factor, density, right? Planar as well as linear density. We'll talk about coordination number again briefly. We'll calculate theoretical density of compounds, right? Why do we know that steel has a density of around 8 grams per cc? If I gave you the crystal structure, could you have predicted that? Polly?
On slide 4, it's definitely homework 4, problem 3. It already says 170 pascals.
It already says 170? Oh.
You uploaded a new one.
Oh, I just uploaded a new one. I corrected it and uploaded a new one. Maybe you just printed it.
Okay.
The original one definitely was wrong. I've corrected it since. Yeah. We'll be able to, if you know, like, for example, see how there's 2 different atoms here? There's the green ones and the black ones, and they're different sizes. We're going to cleverly figure out a tool that says if you know the ratio of those 2 sizes, you can predict what structure it's going to form in, which is remarkable. And then by the end, we'll maybe talk about some 3D crystal lattices and even start talking about how do you define this direction versus that direction, right? There's some rules that we have for that. So to pick up where we left off, we said in the face-centered cubic material, face-centered cubic looks just like this thing here if you ignore the black ones inside. Ignore these 4 black ones on the inside. Just the green ones are an arrangement of face-centered cubic atoms. And we said that how it's drawn here, right, is not necessarily real life. Because in real life, it's a metal. This thing wants to sort of collapse down. The atoms are going to be touching, right? In all these structures, the atoms basically want to touch. They want to minimize distance, right? And so in doing so, this atom, we said, would actually be touching this atom right around here, right? So what we'd like to do, and what we left off is draw a picture of that. And now we want to relate the ionic radii to the lattice parameter. And this might be our first question. Yeah, so this is in fact our first question, which says, all right, if the lattice parameter for copper, which is an FCC metal, is given, it's 3.601 angstroms, what would be the atomic radii in angstroms? So how do we set this problem up? Well, we've got this picture. I need an expression that tells me what the radii is with respect to the lattice parameter. What equation can I write based off of this drawing? So turn to your neighbor and take a stab at it, and then we'll brainstorm. How is radii related to A? Okay, who's got an idea? What's the approach here? Chris.
4r is equal to the square root of a squared plus a squared.
Yeah, right. So what are the? Is it Pythagorean? Pythagorean theorem? Pythagorean theorem, right? Is the one that's for triangles, where basically if you know the sides, a and a, we say that this. Well, since it's the hypotenuse, we'd say a squared plus a squared must equal the hypotenuse squared. And since we know what a is, it's just a and a. So this hypotenuse is going to be root 2 times a. Okay? So now that we know the distance across the face, we know that's equal to, I think Chris was saying it's 4r. It's 4 of our radii. So that's exactly the relationship we need. We need to say that square root 2a equals 4r. Easy peasy. So go ahead and plug this in. I'll give you 2 minutes to do this.
All right. I promise it says submitted. Don't say submitted. I remember I was 16. No, I meant 16.
So what? Simona. That is the last part. And you want the radius. Yeah.
Oh yeah.
Okay, everybody get your answers in. Okay, everybody got answers in? Phone a friend real quick. Did you figure it out?
That'd be incredible.
Did you discover the decimal?
I'm going on, but I put in the.
I'm good to end. This is a quick question. Okay, it should be 1.27. Great, most people get it. I'm sure this is also going to be marked correct. I always give it a range. So the vast majority of folks got this one right. Equals 1.27 angstroms. That's a sloppy angstrom. Right? Okay. So we just did that one. Okay, the next question is, how many atoms are there inside the FCC unit cell? So inside is the key word. If we actually, these things are sitting right on the corners, only part of the atom's inside. So how many atoms are present inside the FCC? Again, this is not FCC because it has the black ones. Ignore the black ones for right now. Otherwise, the green ones are FCC. Let me hold it up. Hey Josh, why don't you come hold it up actually? I'll sketch it real quick. Face-centered cubic, so on this one, in FCC, how many are there per unit cell? Get your answers in. Again, there's 8 corners and 6 faces. Yeah, go take a look. Okay, we're wrapping this up. Everybody get an answer in. Quickly phone a friend. If these are at all remotely difficult for you, if you read the chapter ahead of time, it goes through all of this. So if you're concerned about missing points in class, just read the chapter ahead of time. Okay, I'm ending it. We good? Okay, it's definitely 4. So half the class got this right. So how? Where's that 4 coming from? So there's 8 corners, we all agree, on a cube. And those each have only 1/8 of it inside. Because a cube is sharing, this unit cell is sharing 4 other in plane, right below. And then above it, you've got 4 other unit cells touching. So this is at the junction of 8 different unit cells. So it's sharing between 8. So 8 corners times 1/8 each gives you just 1 atom. And then you've got 6 faces, and these things are right on the face. So they're half in and half out. So you've got times 1/2 gives you 3 for a total of 4. Okay? So 4 atoms per unit cell. Even though you see tons of atoms here, they're not all inside of it. And so we have to count only the ones that are inside by taking the fraction. Okay. For FCC metals, the corner right here and the face are the same exact atom. And in fact, we could actually pick one as the origin. Right? We can pick this as the origin, like it's drawn here. You see it's drawn as a cube. But if we chose this as an origin, we'd get the exact same lattice. What do I mean? Well, if we went from, hold this up, going from this atom back, there's another atom 1 lattice distance away, right? And that's because the origin's here. If we redefine the origin as starting right here, we can still go back 1 lattice parameter and there's an atom here, right? Which would make this one up here the face. This was the corner and this was the face before, but if this is the origin, that's the face, right? So it can be really thought of as 2 interpenetrating simple cubic lattices where they're just located at the corner, right? But it's shifted by 1/2, 1/2. We'll come back to that in a minute, okay? It'll become clear when we talk about the next structure. Next concept is atomic packing factor. Atomic packing factor is just a measure of how compact a structure is, okay? So to figure it out, you just take the volume of the atoms that are inside the unit cell and you divide it by the total unit cell. So what would be the atomic packing factor for FCC is the next clicker question, right? What is the atomic packing factor? So I want you to write the answer in percent. Don't use the percent sign. If you think it's 50, just type 50, right? So how do we do this? You need to figure out what is the volume of an atom. We're going to call them spherical, so that's 4/3 pi r cubed, right, per atom, times the number of atoms. And then we're going to divide this by the volume of the unit cell, right? So to finish this problem, for FCC, we need to go back to our equation up here, which related radii right here to the lattice parameter, right? Because we know that this is going to be 4 atoms times 4/3 pi r cubed, and we'd like to write just a cubed down here, but that's not going to simplify out to a single number because a and r, we need to solve one in terms of the other. But if we recall that square root of 2 times a equals 4r, now we can substitute in there, solve for a, and get rid of our r. So you've got 3 minutes to do that. Oh, take. Yeah. You don't have to know what the radius is. You know it's FCC, so you know that relationship, this right here holds. So you don't need to know the actual number, it's going to cancel out. Okay, one more minute, minute and a half.
Oh no, the question is wait, just go
Yeah, Rob? Okay, yeah, Chris? If, when you take this fraction and you get a decimal, say 0.74 for example, then you type in 74, because that's 74%, right? Okay, so answers in. Okay. I can end, we good? I'm ending. Okay, so 74. Remarkably, 6%. No. 74%. So that means that even in face-centered cubic, which is, a pretty close packed way to pack your spheres together, there's still 26% of the volume which we just can't fill, right? 74% is the highest packing fraction that you can achieve for spheres that are the same size. There's no way you can pack them closer than that, right? And that's placing every atom in a specific location. That's not random like at a bucket of marbles might be. Random packing is like 68%. So we're much better than random packing, and that's as good as we can get. Now, if we had very small spheres to fit in the interstices, which are the spaces in between, then you could go to higher and higher packing fractions, but you're never going to get to 100% if you're packing spheres. There's always going to be leftover space. Next question is, what is the coordination number of atoms in an FCC arrangement? This one's tricky. Remember, coordination number is the number of nearest neighbors at a minimum distance, right? So let's draw this again. We've got... I'm going to draw the ones on the corners like this. And just for clarity, they're the same atom, but for clarity, I'm going to draw the ones on the faces colored in. Right? So, first step to answering a question about coordination numbers, figure out which atom is closest. Pick an atom, right? Something like this guy right here. And you're going to say, what's the closest atom? Is it this one? Well, that's one lattice number away. Meanwhile, this one on this face is a little bit less. Right, that's square root of 2 divided by 2 times lattice parameter. Right? So this is the closest one. So you're going to count up how many of those are nearby. That's the coordination number. So that's the next question. Is it A, B, C, or D? Sorry, let's pull that up again. That's the structure. That structure can be tiled to fill all space. You pick an atom, how many of those types of atoms at that similar distance is close to it? Right? So in this case, the one on that front face and that side face are equally distant. So how many are there that are that same distance? Okay, answers in. Answers in. Again, all of these are right out of the reading. Okay, I'm going to wrap it up. Wrapping up. Okay. I don't know what to tell you. Okay, the answer is definitely 12, right? So why is it 12? Where's that 12 coming from, right? So let's pick one of these atoms and let's draw it. Let's say this guy right here, right? So it's got, at a distance of square root of 2 times A divided by 2, it's got these 3 atoms. So you say it's only got 3, right? That wasn't even one of the options. But you got to remember that this thing is connected. This is at the junction of 8 different unit cells, right? So there's another unit cell. If we change the color to make it a little clearer, there's another unit cell right here, right? I guess, oh gosh, right? And it would have an atom on this face, and it has an atom on that face, but it's the same one. So we can't double count, right? And then it's got atoms below it, right? On that face, on this face, on that perpendicular one. So that's 4 unit cells, but then that atom is also sitting in and out of this plane. It's right on the border. So there's actually 8 of these things, and there's 8 times 23, but they're each in 2 cells. So 24 divided by 2 is giving that 12 number, right? Okay, now you see it. Another way to think of it is that this pink one, in this plane, in the plane of the board, it's got 1, 2, 3, 4. Equidistant. In the plane of the board this way, or perpendicular to the board, I should say, it's got 1, 2, 3, 4, and then in the flat plane it would have 1, 2, 3, 4. Right, so it's got 12 atoms. It's coordinated. Yeah.
So if we chose for starting to be in the face, how do we calculate it?
If you chose the one in the face, you could also do it. So right here, it's got 4 closest to it. 1, 2, 3, 4, and then Perpendicular, it's got 1, 2, and then 3, 4 in front of it. And then flat, it's got 1, 2 on the sides, plus come out 5, 2 more. So it works either way, because I said that those were equivalent positions, so it must work either way. Now, 12, when it comes to coordination numbers, 12 is a huge number. Having 12 nearest neighbors is a huge, it's a phenomenon. Most things wouldn't have that. It's usually 4 or 6 or maybe 8. 12 is a very high number. That's only possible because this is what's called a close-packed structure, meaning those atoms are really packed very, very closely together. Again, that makes sense because this is like the highest volume filling fraction. So coordination number would be 12. Okay? All right, we've lost it.
No more notes.
It's completely gone. And it's back. Okay. But without the 12. All right, body-centered cubic is the next crystal structure we're going to learn about. Body-centered cubic looks just like face-centered cubic in the atoms on the corners, but instead of putting atoms on the faces, you put one in the very center of this thing, right? So if we were to draw, it would look like... We're going to put our atoms at the corners, just like before. And one in the very center, okay? In the very center of the cube, okay? So the question then would be, in the hard sphere model, where would these atoms touch? Before they touched along the face, where are they going to touch now?
Towards the center.
Yeah, like imagine you had one in the center of this thing. I could collapse it all the way until all of these corners at the same side touched it, right? Which means it's touching along what we call the body diagonal. So if we were to connect from that point all the way up to that point, that's the body diagonal, right? And that would have, so if we drew that, it would have one atom in the center. This is touching, this is touching. It'd be like that, right? So we still have this 4R. That's still 4 ionic radii, but what's it now equal to? It's not square root of 2. What would it be? Well, along this bottom face, that is square root of 2. Right? Now this is A. So now our triangle looks like that. It's like I don't know if it's a 30, 60, 90, but it's longer, right? So this is square root of 2A, that's A. So what would this be? What is that distance? That's basically this distance along that line. So what is that? So square root of 3A, right? This is going to give us square root of 3A. Right? So square root of 3A, okay? So that's the lattice parameter relationship to radii for BCC. It's different than FCC, okay? Before it was 4 equals square root of 2, now it's square root of 3. Okay, what is the coordination number of atoms in a body-centered cubic structure? I think this is actually the clearer question. Nope. Next clearer question is the atomic packing fraction. So what would be the coordination number? Guesses? What should it be? This one's easy. It's just 8. You can see that it's surrounded by 8 nearest neighbors, right? So that one's easy. What would the atomic packing fraction be now? This is a quicker question. So for atomic packing fraction, APF, we're going to do, again, 4/3 pi r cubed times the number of atoms divided by the volume of the unit cell. How many atoms are there per unit cell in a body-centered cubic structure? 8 times 1/8 plus 1 in the middle, 2, right? So real quick, get your answer in for atomic packing fraction of body-centered cubic.
And you want to shoot the answer, right? Like without the points, you talked about it last time. So if I got 50%, you want 50, not 45%.
Yeah, write it as if it was a percent.
That's kind of the thing from that specification. Really, so.
It's still better than not. Okay, get your answers in, or phone a friend. Okay, answers in. We good to end? Antonio, what's up? Other person that had to relog in. If you're having issues with the Clicker software, I really apologize. That's out of my control. The Clicker device definitely works. The Clicker software, you can always send me an email and I'll make sure you get your points. I don't want anybody to feel like stressed over their grade with the Clicker issues. That's never my intent with this. The Clicker is just to get people involved, and honestly, it improves how well you learn the material. I don't want it to be something that stresses you out. So if you're stuck and it's frozen, just send me an email and we'll make sure you get your points. Okay, answers in. And it is thinking. 68%, okay. So yeah, these are fine. We're definitely getting it now, right? 68%. So is this more or less densely packed than face-centered cubic? Less, right? This has more open space. The same number, like on an atom per atom basis, this takes up less space. So this is why in the iron wire demo, we start out with ferrite iron and it's body-centered cubic. And when you heat it up to that temperature where it transforms to face-centered cubic, austenite, it goes to a more densely packed structure. Hence why we were warming it up. We expect the wire to keep drooping because it's getting longer. All of a sudden it shrunk. It shrunk because the atoms literally, before our very eyes, rearranged themselves to a more closely packed structure, right? Which is pretty amazing, right? And then it did the opposite when we let it go. When we took the temperature away, it starts cooling down, you'd expect this thing to just go back up because it's shrinking. But it went up and then it expanded a little bit and then it shrunk again, right? Because it went reversibly from face-centered cubic, the dense one, to a more open structure, and then it kept on shrinking, right? Yeah, question?
So for the quicker question, we answered 68 and it said the acceptable value was 0.68. So I don't know why.
I can correct that after class, actually. I can change whether it was in percent or decimal, so don't worry. I will, but send me an email, actually, so I make sure to do that. The next common type of crystal structure is hexagonal close-packed, right? So we have face-centered cubic, body-centered cubic. There's simple cubic, which we didn't even mention, which means atoms are only at the corners. Nothing on the faces, nothing inside. The next one is hexagonal close-packed. And the way to think of it is right here. In this one, if you start out with a hexagonal net, so you've got your atoms at these corner positions along that bottom, what's called the basal plane of this, and one in the very center. These would obviously, again, they would be touching, just like so these things, it would look like this, right? It's in a hexagonal arrangement of atoms, right? And then you're going to stack these hexagonal layers on top of each other. If you place the next layer such that it's exactly over the middle of these triangle up regions, and then the third layer goes back to directly above the original layer, you get hexagonal close-packed. That makes sense? So basically, we have a choice to make. The second layer of atoms, we can choose to set them, they have to be centered over two. Like if I put another layer, I'm definitely going to put my next layer on top of one of these triangles, right? On top of three balls. But this triangle is pointing up, whereas this triangle is pointing down, right? So which one do I choose, right? We have two different sites. Make sense? So we're going to pick one of those. And then if our next layer up, we go back to right on top of what this would be, that is a hexagonal close-packed lattice, right? So it looked like exactly what you see here, right? So again, these three, these would all be touching in that second layer up. And on top of that triangle, when you put the next one directly on top of those, that's exactly above where you started with, right? That's right above this guy. Does this make sense? Any questions on hexagonal close-packed? This clear so far? In the hexagonal close-packed structure, it's no longer cubic, right? This is no longer a cubic thing, so things like calculating volume and some of our distances gets harder. It's not impossible, it's just harder. It's easy for us to think in cubic, it's harder to think of hexagonal. Now, what is the unit cell for this? We already mentioned earlier when we had an arrangement of dots that looked like this. Even though you can make it into a hexagon, we could like draw this thing in a hexagon. We said that the smallest unit cell was actually this guy, because that's the smallest repeatable unit that we can translate around. It's the exact same here. Let me get rid of our atoms for a minute. The smallest unit cell here is not the giant hexagonal prism that you see here. It's actually this thing. That is the smallest repeatable unit cell, okay? So we have new lattice parameters. We have a lattice parameter which we're going to call A on the side, and then C is the vertical one. And C, just looking at this, you can tell C has to be larger than A. If it's a perfect hexagonal close-packed system, there's actually a C over A ratio. I think it's like 1.66 or something that it has to be, okay? The top and the bottom of this thing are called the basal plane. So up here, that would be the basal plane, and similarly on the bottom, the whole hexagonal area on the bottom, that whole thing is the basal plane on the bottom as well. Okay? What is the coordination number in hexagonal close-packed? Well, pick an atom. Let's pick this one in the middle. This one's a little harder to see. Right? That guy, above and below, how many atoms does it have that it's closest to? Yeah, it's going to have the 3 below it that it's sitting on top of, and then 3 above it that are perfectly coordinated around it. So is it 6? No, because also every atom is surrounded by how many?
6.
Yeah, right? So picture like this dark one. It's got 1, 2, 3, 4, 5, 6 all around it, and it's touching those, so it's clearly the closest one. And then above and below, you've got 3 above, and you have 3 below. So it's also 12, right? So just like face-centered cubic, this one also has 12, right? And in fact, if you calculate the atomic packing factor, which you might do on the homework, I haven't assigned the homework for this one yet, you find that it's also the exact same packing factor as face-centered cubic. So even though this hexagonal arrangement and face-centered cubic look nothing alike when you look at them at first, they actually pack the exact same. They're both close-packed structures, and they're equivalent in terms of their packing fraction. Okay? Next up is density. So let's say I know what these atoms are, and they'd actually be touching, right? If I know that this is an iron atom, for example, ignore the black one still. If this is iron, could I figure out the density of this structure? Density in terms of the density that we use as engineers all the time, like some gram per mass, right? How do we do so? It's easy. We use this formula, which is Z times molecular weight, where Z is going to be the number of atoms or the number of molecules per unit cell. We'll start out with just atoms. We'll get to molecules in a minute. So in a face-centered cubic, how many atoms do we have per unit cell? It's 4, right? So it's going to be 4 times the molecular weight of 1 atom, right? So in iron, it's 55 or somewhere around there, right? Then it's going to be volume of the unit cell in the denominator, VC. That would be, again, take the lattice parameter, whatever this was. I think in iron we said it was 3.601. Take 3.601 angstroms, cube it, and now you have a volume, right? That's going to be a volume in angstroms cubed, which is not a normal way to report density. And then you have to multiply that by Avogadro's number. Why do we have to use Avogadro's number? Yeah, because the molecular weight is given in grams per mole. We don't have a mole of substance. We have a per atom substance. We have to turn it into individual atoms, right? So this isn't so bad to do. So let's do it real quick for iron. Let's approximate it, right? What would the density of BCC iron be? It's going to be close to steel, right? We're going to say it's 4 atoms times, what is iron? Somebody have the molecular weight of iron? Anybody?
55.85 or something like that.
55.85 grams per mole. And then we're going to assume that this 3.601 number was not a number I pulled out of my head. I don't know if I think it's actually right, times 6.023 times 10 to the 23 per mole. So when we do this, we're going to get an answer in grams per angstroms cubed, which is not useful. We want to turn that into grams per centimeters cubed. So what you want to do is recognize that this is just the same as 3.601 times 10 to the negative 8 centimeters. 8? I think it's 8 centimeters. I think that's right. Let's check. So if we do this real quick, I get I get 7.94. 7.94 grams per cc, which is about the density of steel. Steel's about 8, right? So that's how you go about doing this. Yeah, Shannon.
So the Z number, is that the coordination number that we find for each?
Good question. It is not, though. It is not the coordination number. It is the number of atoms per unit cell, because this formula, we know that density is mass over volume. So in that the top numerator needs to give us just an amount of mass. So we're going to say the molecular weight, so how much is the atom weight, times how many of those atoms there are. And inside our unit cell, for a face-centered cubic, we said that there's 4. We did the math earlier. And then you multiply it by its mass, right? And since that's a mass per mole, we include Avogadro number on the bottom. So this is how we go about calculating density. Now, steel is not pure iron. It has carbon in it too. And carbon actually goes in between the atoms in the structure in what we call the interstitial sites, right? So for an example, if you see where this black atom is, that is currently an interstitial site in this structure, right? That might be where a carbon would go. And so now you don't have just 4 atoms per unit cell. You have 4 from the iron plus however many carbons you've stuffed in there, right? So the density of steel is actually higher than 7.94 because you've stuffed other things in it, right? Okay. We will do an example of one with a formula soon, but basically, I won't get to it right now. Okay, next up is structure of ceramics. So we've done metals so far. And what do we say about metals? That they share their electrons and they don't really care where they're at as long as they're nearby. And that causes the whole structure to collapse. It becomes very close packed. Ceramics are different in 2 ways, 2 really important ways. First off, you have charges, right? You have cations, which are the positively charged ions, and you have anions, which are the negatively charged ions, right? You have ionic or covalent bonding, which leads to ionic covalent structures, and these are much more complex, right? So there's extremely complex ceramic structures, whereas metals are pretty easy. There's only really 4 they're going to crystallize in, right? Maybe a few more. That's basically it. So both charge and size are going to influence the structure. We know that charge is different. Say rock salt, sodium chloride. You got sodium plus 1, chlorine minus 1. You know that the chlorine added an electron, so it's huge, and the sodium lost an electron, so it shrunk. So you've got really small and really big ions coming together. So when you have a mixture of both size and charge, it leads to a variety of structures. So the first thing we do is we calculate the size ratio, right? We calculate what is RC over RA, where RC is the radius of the cation, RA is the radius of the anion, right? You do that first. And then there's let's say, this ratio is going to give you a number. Now, anions are almost always bigger than cations, right? The anion is the one that picked up an electron. When it adds electrons, it gets bigger. When it loses electrons, it shrinks even more, right? So the anion is almost always bigger than the cation. So these numbers are almost always less than 1, right? There are exceptions. You know, if uranium dioxide, I think uranium might be big enough that it's bigger than the oxygen, but generally this number is smaller than 1. And whatever this number is corresponds to a certain coordination number, right? So I'm a huge Star Wars fan, and the way to think of this is to think about how many atoms can coordinate something. Well, the bigger something is, the more things can coordinate around it, right? So if you have a Death Star, how many TIE fighters can you put around it? Tons is the answer, right? It has a huge coordination number. If you have a TIE fighter, how many Death Stars can you put around it? 2, right? You can have Death Star, TIE fighter, Death Star. That's all you can do, right? So if you have your cation, which is devastatingly smaller than your anion, then you're going to have a very small ratio over here. And your coordination number is 2. This is known as linear, right? Make sense? If it's the other way around, if you can have a very large number, then you can have many, many things around it. That's the concept. So high fraction here, many nearest neighbors, right? And they fit within these ranges, right? So if you're between 0.155 and 0.225, you can have a 3 coordination number. That would look like this, right? You've got these things, and this one in the middle is much smaller still, right? And it's to the point where it would just touch those 3, okay? So in that range, that's where it's going to be happy, right? When I say happy, what do I mean? If it's touching a cation with an anion, if they're touching, it's happy, right? This is really happy, right? Right, it's touching just fine. And there's no empty space, so it's nice and collapsed. This is not happy because it's not touching. Right? Not happy because it's not touching. So that's not a stable structure, unstable. The other 2 will be stable, okay? And so you keep on going. If you have 4 nearest neighbors, we call that a tetrahedral arrangement. So it kind of looks like you've got your base of the pyramid, and these all go up to one point. Again, the atoms in the middle, these would all be atoms around it. So that's a tetrahedral arrangement. That's a terrible drawing. There's better ones if you Google tetrahedra, right? There's 6, which is octahedra. Octahedra is what we talked about in the classroom once upon a time. We said Rob has the 4 people, 2 in the side, 2 front and back, and then he'd say 2, 1 above and below. That's an octahedra. So that's a pyramid with 4 sides, right? But then you can go up and you can go down. So that's an octahedra. 1 atom in the middle surrounded by 6 around the outside. 8 is easy, it's just a cube. And 12 is something called a dodecahedron, which we won't worry about. Okay? The concept clear that basically if I told you the radii of the cation and I told you the radii of the anion, you could divide them, and right away, without knowing anything else, you could say what the coordination of the cation will be. You can say how many anions are going to surround your cation. Yeah, question?
Can you say that again? It's not showing up on the screen. The geometry.
This? I didn't write it yet.
Oh.
Let me write it. So this is trigonal, planar. This is tetrahedral, and this is all in the book. This is octahedral, cubic, and dodecahedral. Okay? It's all in the book. The key concept I want you to take away from this is when it comes to predicting what structure a chemical formula might have, the very first thing is to take into account the charge. We'll get to what you do with that in a minute. The second thing is you divide the size of the cation divided by the size of the anion and predict how many nearest neighbors it's going to have. And this is simply just a size argument, okay? So let's do our first example, and we'll probably end here. The AX type structure is a ceramic structure that has 1 cation and 1 anion. Rock salt is the canonical member of this structure type. It's 1 sodium and 1 chlorine. So where do they arrange themselves? When we take the cation and anion's radii and we divide them, we find out that it's equal to 0.41. Oh, that it lies somewhere in this range of 0.414 to 0.732. I don't know what the actual value is. And that means that its coordination number is 6. So each sodium ion has 6 nearest neighbors that are chlorine. We said that when it has 6, that looks like a cube, right? So if we call this our, which one? Say that one is our sodium, right? We have the 4 in plane with it, 1 below, and there'd be 1 above that is not drawn here, right? Okay, so it has 6 nearest neighbors. Now, because this is a 1-to-1 structure, it's 1 sodium and 1 chlorine, chlorine must have the exact same coordination number. If it had more or less, you'd be off stoichiometry. And so chlorine, the big atom, you can see the one in the middle, has 6 sodiums that are around it, right? This structure looks exactly like the FCC one that we saw before if you took 2 different FCC lattices and you staggered them. Meaning, our FCC lattice from before was like these black points, right? We said corner, 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 and then we had these faces, right? That just looks like an FCC lattice, right? Well, if in addition to that, if you were to start a new FCC lattice, but start it by shifting over 1/2 of a lattice parameter, and then start it right here, Then you'd have a corner outside of what we have drawn here. Now that one would be a face, right? So it's just two interpenetrating FCC lattices, okay? So the question is, this might be a quicker question for next time. No, I haven't yet. So what would be the lattice parameter in terms of R, RC, and RA, right? What would we say? Where are they going to touch? Well, we know that structures are stable when these things touch. The anion touches the cation. So where does it look like? What would it be? Again, this distance from here to here is the lattice parameter. Same thing as this one from here to here since it's cubic, right? So what do we have? A is equal to what? In terms of the radii of our cations and our anions. Yeah, 2RC and 2RA, right? This whole distance here is equal to 1 radii of this, 2 radii of that, and 1 radii of our first one. So 2 cation radii and 2 anion radii. Right? So just like before, if I gave you the radii, you could calculate the lattice parameter, right? Once you have the lattice parameter, you can figure out things like density, right? You can calculate the theoretical density of this compound. And we are out of time, so we'll pick up here next time. Enjoy your weekend.
So how come